Welcome back guys to my YouTube channel. Today we will solve the numericals of class 12th physics chapter 12 electromagnetic induction. I hope you are enjoying the numerical solving sessions of class 12th physics chapters. If you do so, please like, share and subscribe and comment your thought below. So let's look at the first sum. In Faraday's disk dynamo, a metal disk of radius r rotates with an angular velocity omega about an axis perpendicular to the plane of the disk and passing through its center. The disk is placed in a magnetic field acting perpendicular to the plane of the disk, and we need to determine the induced EMF between the rim and the axis of the disk. So solution, there is a disk of radius r rotating about an axis perpendicular to the plane with the angular velocity omega, and the disk is placed in a magnetic field acting perpendicular to the plane. That is, the magnetic field is going in this direction. Okay, and we need to determine the induced EMF. So let's take this point O and let's take this point A. OA is equal to R. When OA takes one revolution, it sweeps out area pi r square, which implies the rate of area swept equal to dA by dt, which is equal to pi r square in how much time? Now we know that time period is the time taken for one revolution, which implies this area pi r square is swept in one revolution, which implies the time taken to sweep this area will be t, which is the time period. And we know that time period t is given by 2 pi by omega, which implies dA by dt will be equal to pi r square by 2 pi by omega will come up, pi gets cancelled, and we can say that dA by dt, that is the rate of area swept, will be half omega r square. Now the induced EMF due to the magnetic field perpendicular to the plane of the disk is given by, in terms of magnitude, E equal to d phi by dt, and we know that phi is nothing but magnetic field into the area. So we know that they haven't mentioned anything about changing magnetic field, so the magnetic field is constant. So we can write d by dt phi as b into a, and as magnetic field is constant it will come outside, so dA by dt. Now we know that dA by dt is equal to half omega r square, so this will be b into half omega r square, which implies that the induced EMF E will be given by b omega r square by 2. I hope you understood this sum. Let's look at the next sum. A horizontal wire 20-meter long extending from east to west is falling with a velocity of 10 meter per second normal to the Earth's magnetic field. What is the value of induced EMF in the wire? We all know that the induced EMF E is equal to B L V sin theta, and as the velocity of the wire falling is normal to the magnetic field, we know that theta is 90 degrees, so sin 90 will be 1, so this formula reduces to BLV. Now we know all the values of B, L and V, so E can be written as B, which is 0.5 into 10 raised to minus 4 into L, which is 20 meter, into V, which is 10 meter per second. So multiplying this, we get the answer 100 into 10 raised to minus 2 volt. This can be written as E equal to 10 millivolt. Milli means 10 raised to minus 3. So this much EMF is induced when the wire is falling with a speed of 10 meter per second normal to the Earth's magnetic field. Let's look at the next sum. A metal disc is made to spin at 20 revolutions per second about an axis passing through its center and normal to the plane. That is solution. A metal disc of radius they have given us 30 centimeter, which we can write 0.3 meter. So this is the radius r, which is 0.3 meter, and is spinning at 20 revolution per second. So frequency is given to us as 20 revolution per second about an axis passing through its center, that is this axis, and normal to its plane, and this disk spins in an uniform magnetic field of 0.2 Tesla. That is, there is a uniform magnetic field which is parallel to the axis of rotation. Now if this is the axis of rotation, so magnetic field B is parallel to the axis of rotation, which is B is given to us as 0.2 Tesla, we need to calculate some of the things. The first thing is the area swept out per second by the radius of the disk. So in one revolution it sweeps out area pi r square as we saw in the first sum, and the disk revolves 20 times in 1 second, which implies area swept in 1 second will be A, which is equal to 20 times into area that is swept in 1 revolution, pi r square. I am repeating this thing again, that we know that the disk revolves 20 times in 1 second, and we know that it will sweep out pi r square amount of area in 1 revolution. So in 1 second it will sweep out 20 into pi r square amount of area. So putting the values, we get area equal to 20 into 3.14 into r square, that is 0.3 square. Now this area will come out to be 5.65 meter square. So we are done with this part. Secondly, they have asked the flux cut per second by the radius of the disk, that is flux per second. We know that phi is given to us as B into A, and we have already calculated the area, and the magnetic field is already given to us. So multiplying them, 0.2 into area, which is 5.65. Multiplying this, we will get flux equal to 1.13 Weber, or you can also write this as Tesla into meter square. And finally they have asked us to calculate the induced EMF in the disk. So we know that E is equal to d phi by dt, and we have already calculated the change in flux per unit second, which is equal to 1.13. So we can directly write it 1.13 per second, therefore 1. So this will be 1.13 volts. Now let's move on to the next sum. A pair of adjacent coils have a mutual inductance of 1.5 Henry. So let's write the solution first of all. And mutual induction is given to us as 1.5 Henry. If the current in one coil changes from 0 to 10 ampere, that is initially the current was 0 and it goes to 10 ampere, in how much time? T equal to 0.2 seconds. So what is the change in flux linkage with the other coil? So let's see first of all what is the change in current. So change in current, that is with respect to time, di by dt is given to us as I, which is changing from 0 to 10 ampere. So final current is 10 ampere and initially was 0 ampere. This current changes in time 0.2 seconds. So here 0.2 will come. So di by dt will come out to be 50. But we need to calculate the change in flux linkage with the other coil. So we know that change in flux linkage is nothing but d phi by dt, and this is equal to the induced EMF, which is equal to the mutual inductance into di by dt, which implies by putting all the values of m and di by dt, we can easily calculate the changing flux linkage. This will actually be the rate of change in flux linkage with the other coil, because the flux is changing with respect to time. So this will be m, which is 1.5 into di by dt, which is 50. So this will come out to be 75 Weber per second. So this is the rate of change in flux with the other coil. I hope you understood this sum. Let's look at the next one. A long solenoid consists of 1.5 into 10 raised to 3 turns per meter. Has an average area of cross section of 25 centimeters square. Okay, so there is a solenoid coil and they have given us the number of turns per meter, n equal to 1.5 into 10 raised to 3 turns per meter, which is having an area of cross section A equal to 25 centimeter square, which can be written as 25 into 10 raised to minus 2 meter square, 10 raised to minus 4 meter square. A coil C consisting of 150 turns is wounded tightly around the center of the solenoid. So a coil C is having 150 turns and it's wounded tightly around the center of the solenoid. Okay, so the N, which is capital N, which is equal to 150 turns for the coil C, is wounded tightly around the center of the solenoid, and we need to calculate first of all the magnetic flux density at the center of the solenoid due to this coil C when the current of 3 ampere is passing through the coil. Okay, so current is given to us as 3 ampere, and for this current we need to calculate the magnetic flux density at the center of the solenoid. So we know that due to current I, there is a magnetic field in the coil which is given by B equal to mu naught small n into I, which is equal to mu naught is given to us as 4 pi into 10 raised to minus 7 into small n is 1.5 into 10 raised to 3 turns per meter into I, which is 3 ampere, and multiplying all these things we get B equal to 5.66 into 10 raised to minus 3 Tesla. So this is the magnetic flux density, or we can call this as magnetic field at the center of the solenoid. Secondly, we need to calculate the flux linkage in the coil C. So B flux linkage we know is given by B into A, but here we are talking about coil C, and the coil C has 150 turns, and this formula is only for 1 turn. So for 150 turns, this phi will be equal to n into BA, which will be n. Capital N is given to us as 150 into B. We calculated 5.66 into 10 raised to minus 3 into area is given to us as 25 into 10 raised to minus 4. And multiplying this, we get the answer phi equal to 2.12 into 10 raised to minus 3 Weber. Lastly, they have asked us the average EMF induced in the coil if the current in the solenoid is reversed in direction in a time of 0.5 seconds. So when current flows in this direction, there will be magnetic field, and when the current direction is changes, the direction of magnetic field will also change. So we know that E average is given to us as, that is the induced average EMF minus d phi by dt, which is equal to, now when the current changes its direction, the direction of magnetic field also changes and the direction of flux will also change, but the magnitude of the flux will remain same. So we can say that d phi by dt, that's it, dt, the flux is changing in time 0.5 second. So 0.5 upon minus of this will be final flux. The final flux was having the same magnitude as of initial flux, which was 2.12 into 10 raised to minus 3 when the current was flowing, suppose in this direction. Okay, so the final flux which was flowing in another direction, because the current direction was reversed, will have the same magnitude but just with a minus sign. So here will be minus of 2.12 into 10 raised to minus 3, final flux minus initial flux, and we know the initial flux was already 2.12 into 10 raised to 3. So this will be twice 2.12, and minus minus will get cancelled, so this will be twice into 2.12 into 10 raised to minus 3 upon 0.5. So 0.5 into this will be 4, and 4 times 2.12 will be 8.48 into 10 raised to minus 3 volts. So this is the average EMF induced. I hope you understood this sum. Let's look at the next one. A surge coil having 2000 turns with an area of 1.5 centimeters square is placed in a magnetic field of 0.6 Tesla. The coil is moved rapidly out of the field in a time 0.2 seconds, and we need to calculate the induced EMF across the surge coil. So solution, they have given the number of turns on the coil, which is equal to 2000 turns, and area is equal to 1.5 centimeter square, which is equal to 1.5 into 10 raised to minus 4 meter square, which is placed in a magnetic field of B equal to 0.6 Tesla. So we know that EMF is given by E equal to minus d phi by dt. Now let's see what is phi. So we know that phi is equal to B into A, but for n turns the flux phi will be n into BA, and the magnetic field and number of turns are constant, so they both will come out. So this will be minus NB into dA by dt. So we know that minus NB dA, that is final area. Now here they have clearly mentioned that the coil is moved rapidly out of the field. So when the coil moves out of the field, the area will become 0 in time 0.2 seconds. So the final area was 0 minus the initial area, when the coil was inside the field, which was 1.5 into 10 raised to minus 4 meter square. So 1.5 into 10 raised to minus 4 meter square, and this thing happened in time 0.2 seconds. So 0.2 seconds. Now putting the value of n and b, we get minus of 2000 into b, which was 0.6, and this minus will, when it will come out, this will become plus into 1.5 into 10 raised to minus 4 divided by 0.2, and calculating this we get the EMF induced across the search coil equal to 0.9 volts. So let's look at the next sum. An aircraft of wingspan of 50 meter flies horizontally in Earth's magnetic field. So solution, we know that Earth's magnetic field goes from south to north, and an aircraft is flying horizontally, and it has a wingspan of, suppose this is our aircraft and it is flying in this direction, and the magnetic field is perpendicular to it, and suppose these are the two edges of the wings, so the wings has a length of 50 meter. Okay, and the Earth's magnetic field is given to us as B equal to 6 into 10 raised to minus 5 Tesla at a speed of, this aircraft is traveling at a speed of V equal to 400 meter per second. So we need to calculate the EMF generated between the tips of the wing of the aircraft. So we know that E is given to us as BLV sin theta, and as always the velocity with which the aircraft is flying is having a direction perpendicular to the magnetic field of the earth. So theta is 90 degree and sin 90 is 1. So this formula will reduce to BLV, and B is 6 into 10 raised to minus 5 into L. The length of the wings is 50 meter, so 50 into V, which is 400 meter per second, and multiplying this we get the EMF generated between the tips of the wings of the aircraft to be 1.2 volts. I hope you understood this sum. So guys, thank you for investing your precious time in watching this video. Share it with your friend and subscribe to my channel.